In this lecture, we shall discuss CPU scheduling. As we know that at any time in the ready queue, there may be more than one processes. Therefore, we will have to choose an algorithm by which one process out of these processes in the ready queue will be selected and will be dispatched to the processor, and that process will be next executing in the processor. Let's see what's the problems involved and what are the algorithms that can be used. Say the CPU scheduler selects one process that are in the ready state and allocates the CPU to it. Here we shall assume that there is a single processor first, and then we will be going to for short discussions when there are more than one processors involved. Now, just to clarify the problem, let me show this diagram that I have shown in the previous lecture. Here is the ready queue. In the ready queue, processes may come from the CPU on timeout. Processes may come from that IO waiting queue, and new processes can come from the job queue. Okay, this is the ready queue. This is the scheduler that we are talking of. That means one of these processes in the ready queue has to be taken, right, and has to be put to the CPU. And when we say a queue, naturally the concept is that we have to take the first one from it and put to the CPU. But how do we maintain the queue? This ordering of it is important. Okay. Therefore, once more, this is the scheduling that we are talking of. Yeah. Now, once more as a recapitulation, the queues are generally maintained as a linked list. Say there's a queue header. This is a pointer to the front. This is a pointer to the rear. Any process that comes into the ready state will be put at the rear. Therefore, this link will be extended. Any process that has to be taken are supposed to be taken from the front. Okay, this is the ready queue. Here is a wait queue that I had shown. Right. Now, let's see, after the process is selected, it is the dispatcher, okay, which gives the control of the CPU to the process selected by the short-time scheduler, and that involves this job: switching of context, switching to user mode if it is an application program by the user, and then start that process, that user process. Now, the time dispatcher takes to stop one process and start another process is called the dispatcher latency, and that's an important point. And naturally, as we discussed, that depends upon the architecture of the system. That means how much support the hardware gives to this dispatching process. Now, before we discuss the methods, let us first see that what are the scheduling criterion. Because when we said that one process had to be selected from so many in the ready state, okay, then there should be some criterion, some basis on which the selection should go, and that's the algorithm, okay, that will decide it. Now, the different criterions are there. First criterion naturally is CPU utilization, that we have to try to keep the CPU as busy as possible. Okay. Next criterion that comes is the throughput, that is the number of processes that completes per unit of time, say 1 minute, 5 minutes, 10 minutes, how many processes completes within that interval of time. Then there is another aspect, okay, that one has to consider. That's the turnaround time. That is the amount of time needed from the time of submission of a process to the time of completion. When we say that the submission of a process, okay, here in fact the submission to the system itself, right? And then the waiting time, that's the amount of time a process is waiting in the ready queue, okay? That is another criterion. And the one more important criterion is the response time. That's the amount of time taken from submission to production of fast response. When submission, we talk of basically submission into the ready queue. Okay. Now let's see. These are the criteria. These are the criteria that have to be taken right into consideration by the algorithm. And when we say that algorithm is doing a job, okay, that means the algorithm has to select one. We'll have to say what is the optimization criteria. Okay, that means which one should we maximize, which one should we minimize. Obviously, the criterion should be that we should try to maximize the CPU utilization, maximize the throughput, minimize the turnaround time, minimize the waiting time, and minimize the response time. Okay, this should be our optimization criteria. Just to make the discussion specific, let us see what we mean by CPU and I/O burst cycle. Now, as we know that as a process goes on, okay, it executes the instructions for some time. That is the CPU. It is in the CPU. The CPU executes instructions. Then it may go to the I/O wait. Okay, when the I/O execution takes place. Right. This is we call the CPU burst and the I/O burst. That means the burst we mean here the amount of time the CPU the process at this instant of time is in the CPU, and the I/O burst means the amount of time the process is waiting for the I/O completion at this instant of time. Or right now, here we have shown a picture where the frequency of processes, okay, in terms of the burst duration have been shown. The burst duration has been shown in milliseconds. As is seen that as the burst duration increases, the number of processes, okay, that has this burst duration increases. Okay, for example, it is say it's peaking here around 2 milliseconds. After that, the number of processes that has burst duration more than 2 decreases, and it comes to more or less quite a minimum around 20. Okay, as we approach somewhat between say 4 and 5. Okay, and 8 it comes to a minimum, and beyond that the number of processes that has burst duration more than 8 is minimum, that is less than 20. I mean, this curve shows that the number of processes having burst duration around this point, okay, is maximum. Below that, the number of processes having burst duration increases with the burst duration, and beyond this point, the number of processes that has burst duration above this point decreases very rapidly till it comes to a minimum, and that minimum is more or less maintained for the higher burst duration. I mean, this curve is important. It's obtained more or less. I should say that this is not exactly. This may not be exactly the nature for all the processes, but this is more or less a representative graph which shows, which helps in determining what should be the policy, okay, of that algorithm for selecting a process that will be executed in the CPU the next instant of time. Okay. Now let us now see the different algorithms. First algorithms is very simple. Okay. In fact, most of these algorithms simple. Nothing is difficult over here. The first come first serve algorithm, and we very much know about it. We face it every day, almost when you go to get any services. So here, basically, that any process that comes fast will get the service fast. Here we have taken an example. Say the process is P1, P2, P3. Let us assume that the next burst time, that means the time that P1 will spend in the CPU in the next instant of time, if it gets a CPU, is 20 millisecond. For P2 is 2 millisecond. For P3 is 3 millisecond. And let us assume that arrival order is P1, P2, P3. Now the Gantt chart for the scheduling, if you take it, for example, that P1 is scheduled at the 0th instant of time, say, then P1 remains there for 20 millisecond, then P2's turn comes because P2 came next, then P3's turn comes, right? And the waiting time for this scheduling at this instant of time for P1, P2 and P3 is 0 plus 20 plus 22, because 20 is the waiting time for P2, 0 is the waiting time for P1, and for P3 it is 22. Therefore, it is average waiting time is 40. Now you can feel very easily that if we use first come first served that scheduling algorithm, the arrival time turns out to be quite important. And as has been shown here, if the arrival order of these three jobs be like this, say P3, P2, P1, in that case the Gantt chart turns out to be say P3, P2, P1. First P3 is served, then P2 is served, then P1 is served. Once more, say this is a 0th instant of time. And waiting time for P1 is 5 millisecond. Waiting time for P2 is 3 millisecond. And waiting time for P3 is 0 here because P3 has come fast and therefore has been served fast. An average waiting time turns out to be 2.66. Okay. Now this immediately says that the average waiting time varies substantially in the case of a first come first served scheduling algorithm. Okay, and there is a convoy effect. Okay, convoy effect means that short processes turns out to be generally behind long processes. By that I mean long process. By that, let us suppose that in this mixture, that is the processes that in the ready queue, one process is there which has a very long burst time, and others having short burst times. That means the first one is a CPU bound job and the others is an IO bound job. Now when the first one is the CPU, then all other processes will finish and will be waiting in the ready queue. Now after the first job is over in the CPU, possibly it goes to the IO wait, then all these processes with short CPU bursts will be completed and immediately will go to for IO waiting. Therefore, the CPU will remain idle. Therefore, you see that either the CPU turns out to be idle or the IO processes turns out to be idle, and that's called that convoy effect, that the short processes follows long process. Now, let's come to the next algorithm, which we call the shortest job fast algorithm, or SJF. Okay, shortest job fast. Here, associated with each process, the length of its next CPU burst is kept. Okay, and we use these lengths to schedule the process with the shortest time. I mean, which means that for example, several processes are in the ready state. The next CPU burst time is kept associated with it. Now, whenever this question of selecting a process from the ready queue comes, we take that particular process which has the shortest CPU burst time. Here, we have shown an example, and we are taking this to be a non-preemptive scheduling. That means by non-preemptive means that once a particular process has been allocated a CPU, that process continues in the CPU until its time, it's timed out or it goes into the IO wait state. Okay. Sorry, I should not say that timed out. It's non-preemptive, therefore we do not time it out. It remains in that IO wait state. It remains in the CPU till the process goes to the IO wait state. That is, we call that non-preemptive scheduling. Let me repeat once more, that we call a non-preemptive scheduling that once a process has been allocated the processor, the process continues in the processor as long as it does not go to the IO wait state. If it has to go to the IO wait state, then only it leaves the processor and goes into the IO wait state, and the next process from the ready queue is selected for that execution in the processor. Now here, let us, in the case of a non-preemptive scheduling, let us see what's happening. Here 4 processes are there, P1, P2, P3 and P4. We have shown the arrival time to be 0 for P1, for P2 is 2, P3 4 and P4 is 5, and the burst time is 7, 4, 1, 4 respectively for P1 to P4. Now, this P1 has arrived at the 0th instant of time, and there is therefore no other process in the ready queue. Then P1 is scheduled here, okay, and then P1 is running. You see that the Gantt chart that P1 starts from here and it takes 7 units of time. Therefore, it goes on till it goes into the IO wait state. Okay. Now, within these 7 milliseconds, P2 has arrived at 2nd millisecond, P3 has arrived at the 4th millisecond, and P5 has arrived, P4 has arrived at the 5th millisecond. And out of this, which are now in the ready queue, since P3 has P3, which has the shortest burst time here, will be allocated the processor. P3's burst time is 1. It has the shortest burst time, therefore P3 has been allocated, and after P3 has going to the IO wait, remaining P2 and P4, both of them has a burst time of 4, and since P2 has arrived earlier than P4, we can break this contention between P2 and P4 in terms of that arrival time, and P2 is given the CPU here, and after P2 has completed its task and goes to the IO wait, P4 has been scheduled at 12 milliseconds. Therefore, this is a complete picture as how for these processes, for this cycle, these P1, P2, P3 and P4 will be scheduled in terms of the shortest job first scheduling algorithm. So we can see that average waiting time here is 0 for P1. Waiting time here is 0 for P1, 6 for P2 because P2 arrived here and has been scheduled here. Therefore, 8 minus 2 is 6. The waiting time for P3 is 7 minus 3, which is, 7 minus 4, which is 3. And the waiting time for P4 is 12 minus 5, which is 7. Therefore, average waiting time turns out to be 4. Now, this is with non-preemptive scheduling. Naturally, there can be a preemptive scheduling also. And in the case of a preemptive scheduling, what we do is this, that if a new process arrives with a CPU burst length which is less than the remaining time of the current executing process, we preempt. Okay, that preemptive SGF therefore keeps track of what is the remaining CPU time that is needed to complete a process which is on the processor in terms of the processes that in the ready queue. If it finds that new process has turned up which has a CPU burst time less than the process that is in the CPU, then the process in the CPU is preempted. That means it is taken out of the CPU, is put back into the CPU into ready queue, and the new process which has the CPU burst time less will be dispatched to the processor. And that's we call that preemption. and that's preemptive shortest job fast. Now let's see that this term that we use for this preemptive SGF is the shortest remaining time fast, or SRTF, shortest remaining time fast. Let us take an example here, that here the processes P1, P2, P3, P4, the arrival time is 0, 2, 4, 5, respective arrival time. The burst time is, CPU burst time is 7414 units, say milliseconds. And let us see how, as per SRTF, the processes will be scheduled. Okay. Now, P1 has arrived at the 0th time, therefore P1 gets the time. Okay. Here in the green, I have shown that the arrival times of P1, P2, P3, and P4 in that violet, we have shown the remaining times, that is the different processes need to complete their complete the process at this cycle. This Gantt chart here shows that what is the occupations of a process in the CPU. So for example, here that P1 occupies the CPU up to this time. So here you see that P1's remaining time is 5, P2 has arrived, okay, and P2's burst time is 4, which is less than the remaining time of P1, which is 5, and therefore P2 is immediately scheduled. P1 is preempted, it is taken out of the CPU, and P2 is scheduled. Now P2 goes on until this instant of time, that means 4 milliseconds, where the P3 arrives, and P3 has a burst time of 1 unit. At this instant of time, P1 has a remaining time of 5 milliseconds, P2 has a 2 millisecond, and P3's burst time is 1 millisecond, and therefore P3 is scheduled. P3 is completed, and at this time P4, you see that once more the same situation for P1 and P2, and therefore P2 is taken and P2 is scheduled. P2 goes on till 7th millisecond, completes its job. Here we have P1 5, and at this instant of time P4 has come with a burst time of 4. Therefore, when P2 has completed, we have the remaining time for P1 5 and P4 4. Therefore, P4 is scheduled here, and after P4 is completed, P1 is scheduled here. And this way, the jobs P1, P2, P3, P4 completes within 16 milliseconds, which is the total time that is needed for P1, P2, P3, and P4. Now, in this case, let's see what is the average waiting time. For the P1, the waiting time is 0 here, and once it has been preempted, it is scheduled here. Therefore, the next it is 11 minus 2, therefore 9. Okay, that is the waiting time for P1. Waiting time for P2 is that it has arrived here, okay, and therefore it has got P2 immediately. It's got the CPU immediately, but it has been preempted here and got the CPU at 5 milliseconds at this instant of time. Therefore, it is 5 minus 4, 1 millisecond. Similarly, it is for P3 and P4, and the total and the average waiting time for P1, P2, P3, P4 turns out to be 3. Now, see that immediately the situation, once more let me repeat, that a process is scheduled from the ready queue depending upon that what is its next CPU burst. Once a process has been scheduled, its remaining CPU burst time is kept track of. If a new process comes which has a CPU burst time which is less than the remaining burst time of the process that is in the CPU, at that instant of time, that process which is in the CPU is taken out of the CPU, and the process that has come with less burst time will be allocated the CPU. But this is only done whenever a new process arrives at a ready state, not at any intermediate point. That's an important point. Okay. Now, the question therefore arises that how one shall know that what is the next CPU burst time for a job. Naturally, one has to only estimate to determine what should be the next CPU burst time for a particular process, and let's see that how it can be estimated. Therefore, the length can only be estimated, and it is estimated by generally that what we call an exponential averaging. Okay, using the length of previous CPU burst. The history of the CPU burst is kept track of, and depending upon the history of the CPU burst, okay, the next CPU burst is predicted, right? Now, to show that how this prediction can be done, we are giving one method which is called that exponential averaging. Here we assume that the Tn is the actual length of the nth CPU burst, that means the last CPU burst. Tau n plus 1 is a predicted value for the next CPU burst. That means the next CPU burst that you're talking of is that at the n plus 1th instant. Okay, and let us assume that alpha is a constant which is varies between 0 and 1, inclusive of 0 and 1, right? And we define tau n plus 1, that means the predicted value of the next CPU burst, to be alpha Tn plus 1 minus alpha tau n. Okay, that is, we define tau n plus 1. Now, let us see that tau n plus 1 once more, let's have repeated alpha Tn plus 1 minus alpha into tau n. If alpha equal to 0, what happens that tau n plus 1 turns out to be tau n, and therefore the recent history is irrelevant. That what time it took in the previous instant of time, if your previous instance of time is unimportant. Okay, the most recent history is unimportant, and it depends upon tau n only. That means the predicted value in the previous instant of time. Okay, and if alpha equal to 1, then tau n plus 1, that means the predicted value of the next CPU burst is taken to be the actual last CPU burst. Therefore, that actual last CPU burst only counts. Now, if you expand tau n plus 1, okay, by replacing tau n by tau n's expressions, tau n naturally will be alpha Tn minus 1 plus 1 minus alpha into tau n. Let us see what we get. It turns out to be alpha Tn plus 1 minus alpha into alpha Tn minus 1 plus 1 minus alpha tau n minus 1. Okay, and this gives us that alpha Tn plus 1 minus alpha Tn minus 1 plus 1 minus alpha square tau n minus 1. That's, now we can replace tau n minus 1 by its expression, okay, the way that we have replaced tau n, and if we go on doing it, we'll get an expression of this form, that tau n plus 1 is alpha Tn plus 1 minus alpha into alpha Tn minus 1, and the jth term turns out to be 1 minus alpha to the power j into alpha Tn minus j, plus the last term is 1 minus alpha n plus 1 to the power n plus 1 into tau 0, which is the initial predicted value. Okay. Now, let us see the situation. Now, since alpha and 1 minus alpha are both less than or equal to 1, you see that each successive term will have less value, less weightages than its predecessor. Okay, therefore, depending upon the value of the alpha, how much of the past history, okay, we are giving importance to, that can be determined. You see that if alpha is closer to 1, that we are going for shorter history. the later terms in the series will be more or less insignificant. Therefore, alpha closer to 1 implies that we are going for a shorter history, and if we make alpha closer to 0, it means that basically we are going for a long history. Okay. Therefore, by choosing alpha properly, and we can predict what will be the value of the next CPU burst for the next instant of time, and this predicted value can be used for that this algorithm. Okay. Now, let us see that another algorithm which we call that priority scheduling. Here what we do is this, that a priority number, which is basically an integer, is associated with each process. Usually smallest integer means highest priority, and those are integer values that we take. CPU is allocated to the process with the highest priority, and we make it preemptive. That means if a higher priority job is in the queue, job queue, then the lower priority job is preempted and is sent back into the ready queue. Okay, therefore we can make it preemptive. We can make it non-preemptive also. That means that once it is allocated, it remains in the CPU even though a higher priority job arrives in the ready queue. Now, essentially, if you see that SGF is basically a priority scheduling, where the priority is the predicted next CPU burst time. The lower the predicted next CPU burst time, the higher will be the priority, and that process will get the processor. Okay, the SGF is essentially a priority scheduling where priority is a predicted next CPU burst time. Now let us see what can be the problem of this priority scheduling. The problem is starvation for the low priority process. See, the priority is low of a particular process, and if all the time some process with higher priority goes on coming into the ready queue, then that process which having a lower priority will never get a crack at the CPU, will never get the CPU, and therefore it will wait in the ready queue indefinitely. Okay, then what can be done about to circumvent this problem is that we increase its priority on aging. Therefore, that we note down the time a particular process has arrived in the ready queue, and the time elapsed, its priority is promoted, so that once it will, at least after a reasonable time, that particular process gets a CPU. Okay, that is the priority scheduling. And let's come to what we say, what we describe, another scheduling algorithm. We call that round robin scheduling. Okay, in this round robin scheduling, what is done essentially, it is used in the case of a time sharing system. By time sharing, we mean that at the time of dispatching each process is allocated a small unit of CPU time. Okay, that whenever a process is dispatched to the CPU, associated with each process, a time quantum is attached. Okay, and that time quantum is, so for example, the queue here is usually 10 to 100 milliseconds. Now, if there are n processes in that way, what happens exactly is this, that at the end of this time quantum, if within the time quantum, if the CPU completes, if the processes completes the job, then naturally it goes into the exit state. If it asks for an IO, then it goes to the IO wait state. But if it consumes that entire time quantum and still needs a CPU, then it's brought back on timeout interrupt. That means a timeout interrupt is given. The scheduler takes immediately care of it. It takes that particular process out of the CPU, puts back into the ready queue. Another process from the ready queue is then given, is then dispatched to the processor. Now, that way, what we are doing is that we are time sharing the CPU amongst the processes. And if there are n processes in the ready queue, that no process waits more than n minus 1 into q time units. That's the maximum a particular process will be waiting amongst the processes which are in the ready queue. Okay. Now, let's see that what can be the performance of it. The performance that if Q is large, essentially it will behave like a FIFO. That means it's non-preemptive, first in, first out. And if its Q is small, then there can be problem. If it is too small with respect to the context switch time, then the performance naturally will degrade like anything. And therefore, the thumb rule is this, that 80% of the CPU burst should be the shorter than Q, that the time quantum. Right. Now, let us say that the gist of the round robin scheduling once more, that every process is given when it is dispatched to the CPU, a time quantum is attached. At the end of the time quantum, if it still needs the CPU, naturally the timer interrupt comes. The CPU, the process is then taken out of the CPU and put back into the ready queue. Another process is taken from the CPU and is given the CPU time, right? This way, essentially what happens that in this case, that every process, if there are n processes in the ready queue, then every process is assured of a CPU time within a time interval of n minus 1 into q, where q is the time quantum. Now, the performance that what should be your time quantum, that is dependent upon that these observations, that if you make q too large, then it will behave as if that it's a FIFO, and if the time quantum is too small, then compared to the CPU context switching time, in that case, the performance will be severely affected. Therefore, we go for a thumb rule, which has been found on observations, that if we choose the Q such a way that 80% of the CPU burst is shorter than Q, in that case, the behavior turns out to be more or less okay. Now, let us take an example of say that round robin scheduling. Here, so 5 processes are there, P1, P2, P3, P4 and P5. Okay. Let us concentrate here first, the top part of this slide. Say there are 5 processes, P1, P2, P3, P4 and P5. The burst time is 65, 27, 48, 55 and 10 respectively. And let us assume that the time quantum is 20 milliseconds. Okay. Now, in the case of a round robin scheduling, and let us assume that all of them have come more or less together, which means that all of them are contending in for the CPU, and RR scheduling has been implemented. In that case, you see the first P1, then first P1 will be given the CPU time. At 20 milliseconds, P1 will be taken out. It will go back to the ready state, okay, and P2 will be taken and will be put into the CPU. Now, when I say that they have more or less come in the same time, I'm assuming that this is the order, okay, that is P1 first, then P2, then P3, P4 and P5. That's the order they have come, okay. But more or less at the same time in the sense they're contending now, right? Then P2, here the P2 has got the CPU and P2 has been taken out of the CPU at 40 millisecond and P3 is given the CPU. Then P3 is executed up to 60, then P4 is executed, and then P5 is executed. Now, when P5 comes, you see that P5 completes. That means this is a CPU burst, and after that, either it goes for I/O or it has completed. Therefore, P5 is automatically comes out of the CPU and goes into the I/O wait state or goes into the exit state. And then in the round robin, P1 gets the CPU once more. Okay. Here the P1 gets the CPU for 20 milliseconds once more. Then P2 gets the CPU and P2's remaining time, that means 7 milliseconds, it exhausts and P2 goes to the I/O wait state possibly and P3 gets the CPU. Right. This way the entire scheduling goes on. You see that P1 completes by getting CPU time first here, then here, then here, okay, 60 milliseconds, and then the rest 5 milliseconds at the end, and P1 either goes to I/O wait state or the exit state at this point. Right. This is what is the round robin scheduling. Now let us see that what are the features of this round robin scheduling. You see, every process here has the impression that he owns his own machine. Okay. You see, possibly to reduce speed. Now, the entire CPU time, say here, has been divided into chunks and have been given to all the processes that is contending. Therefore, as if every process, say P1, P2, P3, P4, and P5, just has the impression that as if he owns his own CPU, okay, but with reduced time because the total CPU time is distributed amongst all these processes. Okay, and therefore you can see that for say interactive kind of jobs, possibly this can be a good algorithm. Now, the performance of the round robin scheduling is that it has a higher average turnaround time compared to the shortest job fast, but better response time, and therefore when the question of response comes into the picture, like say an interactive jobs, then possibly that round robin scheduling will be better. Okay, that's what the round robin scheduling. Therefore, in this lecture up to this, we have discussed the scheduling policies, some scheduling policies. We would like to stop here today, take a break and take over the scheduling, other aspects of the scheduling and say some more scheduling algorithms in our next lecture, including that what happens if we have more than one processor. That's all.